there are a few keywords here in the title that I'm going to cover in this presentation. So the keywords are formation, stability, solid electrolyte interface or SEI, and sodium-ion battery. So I'm going to cover these keywords one by one, and probably most of you are very familiar with these topics, but I'm gonna maybe shed a little bit more light into these topics, and then we can have discussion at the end. So we start with sodium-ion batteries first, the last keyword here, which probably you all are very much aware of motivations to work on sodium-ion batteries. But to briefly highlight that and put things into perspective, here is what you see a figure from a report which was published by McKinsey a few months back, showing how much batteries is needed in upcoming years, and how bigger the size is in a way compared to a few years back. And you see that the demand is divided for different area in the world. And as you see, China was dominating the battery market and is dominating battery market today, and will most likely dominate in upcoming years. But the expectation is that Europe and US and the rest of the world also will be much more active in cell production. And here is only about lithium-ion batteries. But you see, the increase is quite significant, that we are expecting almost 30% increase in lithium-ion battery cell production in upcoming years. You might ask, what does it mean and what are these numbers? If we say that back in 2022, that we had almost 700 gigawatt hour cell production, and we are expecting to have almost 5,000 gigawatt hour cell production in upcoming years. If you could put this in perspective to understand, I could give you one example that probably most of you are familiar. But Northvolt, a company which unfortunately didn't manage to continue to become successful, and they failed and filed bankruptcy a few months back, as probably you have seen in the news. But the plan was to have a gigafactory of 32 gigawatt hour cell production here in northern part of Sweden. So from this might be easier to put things in perspective, that for one factory, northern Sweden, with all those challenges that ultimately led to bankruptcy of Northvolt, the goal was 32 gigawatt hour, and that was a huge factory. So if we convert back to these numbers, what we are expecting is that we need almost 120 to 150 gigafactories around the world in upcoming years. Of course, it's not going to be all in Europe or in one location, but if you look at it around the world, 120 to 150 of those gigafactories is quite a big number. So the question here is that, where do we get material for to produce lithium-ion batteries in all those gigafactories? And this is already shown that there is no enough materials for those gigafactories in upcoming years. And what you see on the left is the demand and the supply for lithiums. And as you see, the gap will be bigger and bigger when it comes to supply and demand of lithium. And this is not only the case for lithium, but also for cobalt, nickel, natural graphite, and synthetic graphite that you see in the middle. And this is mainly because that some of these elements are sourced only in limited geographical area, only in few countries, and they are not that abundant. Of course, you may ask, or you may say that, okay, we need to do more mining, which is definitely interesting and relevant topic. And you see on the right how many more mines basically we need for each of these elements to cover the demand. But the point or the problem with mining is that it takes time, much longer time than building a gigafactory. When we talk about mining, we are talking about roughly 10 years timeline from start until the mine becomes in full production, while gigafactories can be built in 3 to 4 or 5 years maximum, and up and running. So this is a challenge, and of course there are other challenges with mining. But if you put all this into perspective, one solution would be to diversify chemistries used in batteries. And there the idea is to use more naturally abundant elements. For example, you can see on top left, the green area, these are the elements that are abundant in nature. So there will be less concern in terms of access to those materials if you could make competitive batteries based on those elements. So instead of lithium, you can see we could potentially use other cations like sodium, magnesium, calcium, and potassium. And of course, each of these chemistry has own challenges and problems, but just in terms of availability and sustainability, these could be options. And in terms of transition metals, instead of nickel and cobalt, if we could use iron, manganese, and titanium, that would be one major step to make sure that we diversify chemistries used in batteries and we have access to elements for batteries. So this is basically the motivation for sodium-ion batteries. And there are many groups, as you know, there are many groups, research groups around the world working on sodium-ion batteries since many years ago, and it has become a very important topic in the last few years, especially by the fact that some industries have shown interest and have produced commercial sodium-ion batteries. So it's not only research anymore, but also a valid solution that will be commercialized more and more in upcoming years. With this brief introduction, what we have been doing over the last 10 years in my research team at Uppsala University to work on sodium-ion batteries. And you see here 4 major pillars that we have been working on when it comes to sodium-ion batteries. So 10 years ago, when we started on sodium-ion batteries, this was considered very much future chemistry. It wasn't something for really commercial production, but something for the future. But the picture is changed today, and you see more commercial activities around sodium-ion batteries. We have been using a number of different in-house and synchrotron-based characterization tools to understand chemistry and electrochemistry of sodium-ion batteries. We have been working on development of few different active materials, cathode and anode, but also electrolyte materials. And then we had a spin-off called Altris in Uppsala, which has been working since 2017, trying to commercialize sodium-ion batteries. So if you go to the topic of this presentation, which is around formation and stability of SEI in sodium-ion batteries, what you see here is a schematic picture of number of different aging mechanisms in batteries, in lithium-ion batteries, and you have the same or more or less similar aging mechanism in sodium-ion batteries. The purpose here with this schematic picture to show you how complicated aging is in batteries. So there are many different reactions occurring the same time, which could lead to aging. So it is a difficult topic to understand aging because these reactions could happen at the same time. So it's very difficult to mimic the reality in the cell and to try to understand all these reactions. So it's quite fascinating to see that after almost 40 years since lithium-ion batteries were commercialized, we are still working on understanding aging in batteries. And it's not fully and completely understood yet, and it's not completely addressed yet. So as I said, because it's very complicated. So out of this complicated picture, I'm gonna just talk about only and only SEI, which is very relevant topic for aging in lithium and sodium-ion batteries. A very brief information about SEI, or solid electrolyte interface. It is a very thin layer, few nanometer, made of inorganic and organic species, crystalline and amorphous components, and it is very essential to make batteries kinetically stable. Because as you know, the electrochemical potential of most anodes like graphite or hard carbon is below electrochemical stability of electrolytes, which means that batteries are not thermodynamically stable. This is very interesting. We are working with a system which is not thermodynamically stable, so we need to make it kinetically stable. So you could think of, for example, if you expose a pure aluminum to air, there will be oxide layer formed on the surface of aluminum, and that oxide layer will make bulk aluminum stable, so there will be no further corrosion. So we expect something similar here. By this SCI, basically, we make the system stable to make sure that there is no decomposition. But the challenge here is that there has to be ion diffusion through this layer to have a battery. And that's makes it a very complicated system to form and to understand. There have been so many studies on understanding SCI in lithium-ion batteries, but to highlight the issue here a little bit, when we talk about sodium-ion batteries, not everything is exactly the same as lithium-ion batteries. The reason is that, of course, there are differences between electrolytes and electrode materials used in lithium and sodium-ion batteries. So as you see here in these pictures, the atomic radius of sodium and lithium are different, which leads also to different solvation structure, different conductivity and different viscosity, even if you use the same solvent and the same anion, but only changing lithium to sodium, that leads to different properties of electrolyte solution. Because of this, we cannot really copy and paste all our learning from lithium-ion batteries to sodium-ion batteries. So we need to understand the differences and to see how SCI is different in sodium-ion batteries compared to lithium-ion batteries. As I mentioned, there are a number of points that we expect from SCI in batteries. We expect ion diffusion, no electron conductivity. It should block any solvent diffusion, and ideally it should form with very little irreversible reaction, very little irreversible decomposition of electrolyte. So the first cycle is very efficient, and it is expected that this SCI remains intact. Basically, there is no decomposition of SCI over lifetime of battery at different conditions, different temperature, different cycling rate, and so on. Because if the SCI is decomposed, then there will be new layer of SCI formed, and that is in expense of charge consumption and electrolyte consumption, which leads to aging and capacity fading. So ideally, we form SCI at the factory during the first few cycles, during formation cycles, with very little irreversible capacity, and that SCI remains stable and intact over lifetime of battery. One specific challenge here is the stability and chemical stability of SCI, because as you expect, when SCI form, all those species that form SCI, they could actually be dissolved in electrolyte solution. As an example, if we say that lithium fluoride or sodium fluoride is one SCI species formed during electrolyte reduction, lithium fluoride or sodium fluoride could be dissolved back into electrolyte solution. And that basically means that we need to reform or we need to form this species until there is no solubility of these species in the liquid electrolyte. So basically the electrolyte becomes saturated by all these species. So here we have been trying over the last few years to understand the solution of SCI, how this leads to aging specifically in sodium-ion batteries, and how we could address this issue. This is one very interesting example published by Stefan Harris a few years ago, highlighting this issue that if you look at different SCI species in lithium-ion batteries, you could measure actually solubility of these species in, as an example, in DMC solvent, and you could see that they have different solubility. So ideally, your SCI should be formed by a species that have very low solubility in the solution. So you could basically use some electrolyte and tune it to form a species that are less soluble. But as I mentioned, this is only one factor out of many factors needed for SCI. But it's still very important to understand this factor and see how we can improve it. So what we did a few years back, we tried to work with model cells. And the reason is that if I go back to that complicated picture of aging in batteries that I mentioned a few slides back, if you use full cells with like practical electrodes like hard carbon and any cathode, then there are many different aging mechanisms. So it might be difficult to distinguish SCI aging from other aging mechanisms. So instead, what we have been trying to use is to use metallic foils as working electrode. This could be platinum foil or gold electrode, or it could be a glassy carbon. That was the first step, but later we also moved to practical electrodes like hard carbon, or we tried to use model electrodes like carbon black electrodes with rather high surface area to increase the amount of SCI formed. And to try to understand what happens with SCI formation and dissolution. So basically, we form SCI on working electrode, and then we give some time to the SCI with no external potential or current, and then we see part of this SCI is dissolved back into the electrolyte, and then we try to understand this. What you see also here, we have added a membrane between the negative electrode and positive electrode. This membrane is to make sure that there is no crosstalk between the electrodes, because the issue with sodium metal or lithium metal as counter electrode is that the plating and stripping efficiency is not high if we use carbonate-based electrolyte, which are the most common electrolyte, which means that during each cycle, when you do plate and strip on the counter electrode, then there are some side reactions formed, and those side reactions could actually move towards the working electrode, and that could influence the composition and the solution and performance of SCI. So by having this blocking membrane, we try to block any crosstalk between the electrodes. So on the left, you see the schematic picture of the cells that we have been using, as I explained. On the right, you see different electrochemical protocols that we use to mimic different aging in batteries. So for example, on top one, you see the cell was cycled for a few times, but then the cell was stopped at almost 0.1 volt, very low voltage, where SCI had formed already, but by keeping the cell at that potential and leave it for extended time with no external current or potential, we make sure that the electrode is at low potential. So if there is any possible reaction between electrode and electrolyte, that could happen simultaneously in the cell. And then after that, we basically discharge the cell again to see if we can form more amount of SCI. If we can, that indicates that part of this SCI was dissolved during this pause or relaxation time, and that's why we can consume more current or charge to form SCI again. On the second protocol, for example, you see that after the pause, we try to take sodium out from the working electrode. And then again, here, by measuring the amount of charge before and after pause, we can understand if SCI was exposed to any of the aging mechanism and if this dissolution happened. And on the third one, as you see, the cell was stopped at high potential, which basically means that there should be no intercalated sodium if we use carbon black or hard carbon. So what is only left there is SCI species. And then after the pause, we try to destroy the cell. So by using different protocols, we try to understand different aging mechanisms related to SCI and related to negative electrode. So you see in the below, in the bottom, you see a schematic of few possible agings related to the negative electrode. On the left, you see that when the electrode is sodiated and we pause the cell, and after the pause, we see that some of lithium are lost. This could indicate that some of sodiums are diffused into current collector, for example. This is so-called sodium trapping. If sodium is diffused into the current collector and we cannot extract it easily in upcoming cycles. The middle one is when sodium actually is lost because there is leak current at SCI. Basically, sodium ions can diffuse back from SCI while there is no external potential of current, and some of those sodiums are lost. And on the right, you see the solution of SCI species at different state of charge at sodiated or dissociated states. So by using these models and different protocol models, so we got results for different electrolyte systems for both sodium and lithium-ion batteries. So I'm not going to present all those data, but highlighting only few of them here. So what you see on top left, this pause was applied for different variation of time. So by this, we could see that on the bottom figure that how much capacity is lost during the pause. And we can see a linear relation between capacity loss and a square root of pause time, which indicates that this is diffusion-based mechanism. Basically, when we give time, some of SCI species are dissolved back and they can diffuse into the electrolyte solution. On the right, we can see that this capacity loss is related to the volume of electrolyte. There's linear relation between the electrolyte volume and capacity loss, which again confirms the idea that part of SCI is dissolved back into the liquid electrolyte. And as you see, the larger the volume of electrolyte is, the more of SCI is lost into the electrolyte solution, which makes sense when we have larger volume of electrolyte. And using different analytical tools, including XPS and GCMS and so on, we could see that the electrolyte composition is changed before and after storage or after pause. You see in the middle and bottom that there are some minor peaks. They are very minor and perhaps difficult to observe, but still possible to see minor changes before and after storage, which again indicates that SCI dissolution is occurring during the pause. So we applied this model system and the electrochemical methods that I explained for different electrolyte solutions. Here we see some results on 3 different salts, PF6, FSI, and TFSI in 3 different solvent mixtures. Of course, one could use different electrolyte mixtures, but we just wanted to demonstrate this method as a possible way to characterize SCI aging in different electrolyte solutions. So the outcome, as you see here, is that the least SCI dissolution was in electrolyte based on ECDME in TFSI-based solution. On the left, you see that the majority of irreversible capacity is basically achieved during the first cycle as expected. That's when the major part of SCI is formed during the first reduction. But as you see in the dashed line area, there are still some reduction charge consumed to further form SCI in the following cycles. So this also highlights that depending on what electrolyte chemistry we use, maybe the electrolyte reduction and SCI formation is not fully complete on the first reduction, and it may require further reduction in the following cycles. And the reason, as I said, one of the reasons could be that part of the SCI formed during the first cycle could be dissolved back into the liquid electrolyte solution. So by showing this issue, what we tried to do next step was to see if we can mitigate this issue to some extent, at least. What you see here is, again, a schematic picture of SCI. And what we try to do is to add some of this SCI species into the electrolyte in advance before starting the cell. So the interesting thing here, as you see in the table in the middle, if you look at a few different SCI components, like lithium fluoride versus sodium fluoride, or lithium carbonate versus sodium carbonate, you can see that the solubility of these species are very different depending on what solvent we use. If it's water, of course, it's much higher, and it's one case which is very easy to measure. But when it comes to organic solvents like PC and ECDC, of course, it's more difficult to measure solubility, but still you can see that the numbers differ depending on what species we are measuring. For example, sodium fluoride has slightly higher solubility compared to sodium carbonate. Another interesting point here is that lithium species, at least these two lithium compounds, have much lower solubility compared to sodium compounds, which is again in line with the fact that we expect that the CI species of sodium-ion batteries are more soluble than lithium-ion batteries. And this is a bigger problem for sodium-ion batteries compared to lithium-ion batteries, but it is possible to address this issue, but we need to understand the system and address it properly. So we use these electrolyte species as electrolyte additive. Basically, we added those species in advance to the electrolyte solution. For example, we added lithium fluoride to the solution to see if that influenced the composition of SCI and the aging of SCI. Just to highlight again here, this is a very model system. We know in reality, SCI is way, way more complicated than this. There are organic species in SCI, which is very difficult to synthesize in advance and add them beforehand to the electrolyte solution. But we try to, again, use model system to mimic the situation. So by adding sodium fluoride and sodium carbonate to the system, we did the same type of experiment to measure the solubility and aging, but we also did some XPS measurement, synchrotron XPS, to see how the composition of SCI has changed. So if you look at the green spectra in the bottom, those are in ECDC-based solvents with, of course, sodium PF6. We don't see much changes when we add sodium fluoride in advance. So basically, the spectra and the SCI composition is more or less the same, no matter we add sodium fluoride or not. But if you look at PC, you can see that the composition of SCI is influenced when we add sodium fluoride. There is more sodium fluoride in the SCI when we add sodium fluoride in advance. And this is in line with this previous table that I mentioned here. If you see lithium fluoride, the solubility of lithium fluoride in PC is higher than that in ECDC, which means that we expect more solubility of lithium fluoride in PC, which means that when we add sodium fluoride into the electrolyte solution and we saturate electrolyte, then we don't allow sodium fluoride that is electrochemically formed to be dissolved in the electrolyte solution. That remains in the SCI, and then we can detect it by XPS. While in EC, the solubility is very low, and perhaps the addition of sodium fluoride is not gonna have any major impact on the composition of SCI. So this was just few examples to highlight how we have been trying to understand SCI, the solution in sodium-ion batteries. Another related topic that I want to highlight here when it comes to SCI and sodium-ion batteries is related to this salt, sodium bob, probably you are very familiar with the lithium bulb that has been used for lithium-ion batteries. The interesting thing with sodium bulb is that it is very difficult to solve it in most common solvents. Sodium bulb actually was first demonstrated by Stanley Whittingham some years back, but it wasn't used in any battery application because it's not soluble in carbonate and ether-based electrolyte. But then we found that actually we can dissolve sodium bulb in alkyl phosphate solvents like TMP and TEP. And then we tried to understand how this electrolyte works in terms of STI formation and in terms of stability of STI and in terms of aging in sodium-ion batteries. So by using this electrolyte, we could form a non-flammable fluorine-free electrolyte, which provide a conductivity of roughly 5 millisiemens per centimeter, which is not very high and definitely lower than a standard electrolyte based on carbonate, but it's still quite good and acceptable ionic conductivity, especially for low C rate batteries like C over 3, C over 2 that can easily be handled. And we have been working on this electrode in the last few years, aiming to improve safety and sustainability of sodium-ion batteries. The interesting thing with this electrolyte is that if you make a full cell of hard carbon versus Persian white using this electrolyte, sodium bulb in TEP, on the left, you see the first cycle and second cycle in 2 electrode cell, and then on the right, you see the three electrode measurement showing each electrode individually. So the interesting part is if you look at the first cycle, I don't know if you see my mouse, but somewhere around from 1.5 to 1.7, there's a distinct feature on the first cycle when we charge the cell, when basically form SCI. This is very distinct feature for sodium bulb decomposition. From these results, we can learn that sodium bulb is decomposed very early in this electrolyte solution, perhaps way before TP. But we found that this electrolyte itself, as with no additive, is not really stable for long-term cycling, and the first cycle Coulombic efficiency is not really high. So this needs to basically, the electrolyte needs to be optimized to be practical for any commercial lithium-ion batteries. One way is, of course, to use additives to optimize the electrolyte. And by using additives, what you do, basically, you influence the SCI formation. So if there is any additive, like let's say VC, for example, that is decomposed before sodium bulb, then the SCI becomes VC based very much. Then we will basically can address this issue that sodium bulb itself cannot form any efficient SCI. Another thing that we could do, and that's interesting topic that we try to understand to see what is the relation between this electrolyte composition and formation protocol. Because as we see here, as I mentioned, it's very clear, distinct feature at around 1.5 to 1.7 where sodium bulb decomposed. So we try to use different formation protocol that you see here. In the base one, basically the cells were galvanostatically cycled, very standard one, with the distinct feature that I mentioned that you see sodium bulb is decomposed first. But we used 2 other formation protocol. In one protocol, we call it a skip, the green one. We quickly go actually to 3 volt to skip the composition of sodium bulb, and that's why we call it a skip protocol. So by moving to 3 volt in full cell, which basically means that hard carbon suddenly is exposed to very low potential, so the whole electrolyte will be decomposed. So this will include sodium bulb and TP together. So it's not a slow decomposition where sodium bulb is decomposed first. The other option is hold, that we keep the cell actually at around 1.7 to make sure that we decompose sodium bulb as much as we can to show the weakness of SCI in that case. So by using these three different protocols, we measured the first cycle Coulombic efficiency and also the Coulombic efficiency in the following cycles, and the discharge capacity and capacity fading for all these three protocols. So here you see the results, and for each cell, we basically tested at least, or for each chemistry, we tested, and each protocol, we tested at least 3 different cells to make sure that we have full control on the error bar and we have reproducible result. And this is a major issue actually in battery literature. So I really recommend everyone here, if you're working with batteries and if you're making cells, make sure that you make at least 3 cells for each experiment to present the error also in the measurements. So with this, I'm going to finish my presentation and basically highlight that what we have been doing in last few years is to try to use model systems to understand SCI dissolution. We try to simplify battery cells using model electrodes, model electrolytes to distinguish aging mechanism and to try to understand each one by one. And we have been using a number of different characterization tools, especially in-house and synchrotron-based XPS, to understand the composition and stability of SCI in sodium-ion batteries. So the question here is still how we could design an efficient electrolyte solution for sodium-ion batteries, and what we can learn from previous knowledge on lithium-ion batteries, and how we could use this knowledge and how we could transfer this knowledge to sodium-ion batteries to formulate efficient and stable electrolytes for sodium-ion batteries. With this, I would like to thank the sodium team at Uppsala University. We call ourselves Big Cats, and Big Cats is coming from big cation, sodium and potassium, that we have been working last almost 10 years. And also to thank the funding agencies for financial support, enabling us to run all these experiments and projects.